first of all, CPU scheduling means making the maximum use of our CPU. Sometimes what happens is many processors will come to run. In that time, some processors will be put into the waiting state. So at that time, what happens? The CPU becomes idle. So we are not making use of CPU at the maximum, and the time gets wasted. So this is for this purpose we are introducing some scheduling algorithms to make the CPU for the optimal use. So that is called CPU scheduling. So what the CPU scheduler? What is the CPU scheduler is? There will be n number of processors like P1, P2, P3, P4, and so on. There will be many more processors. So this scheduler will decide which process has to be allocated to the CPU. If one process is allocated to the CPU, and simultaneously what happens, other processes will be put into the waiting state. So this happens alternatively. So the CPU scheduling decisions may take when a process switches from a running to a waiting state. That is first case. Another is when it is switching from the running to the ready state, and the third one is from waiting to ready state, and then it terminates. So scheduling is of two types. One is non-preemptive, and the other is preemptive. So what is preemptive is uh, the CPU scheduler or that system can take control over the processing methodology. That is, it can force a process to terminate out of the system. So that is called preemptive. In non-preemptive, we cannot the system cannot take control over terminating particular process. That is the difference between non-preemptive and preemptive. So in preemptive, forcibly the process gets terminated without without completing the process. But in non-preemptive, no other go, the process has to complete its process. Uh, However, the time takes very long, like that. Then how these scheduling algorithms are selected. So there are many factors on which this CPU scheduling algorithms are selected. There are many CPU scheduling algorithms like first come first serve, round robin, and so on. There are many. Then how to choose it? That is based on these criteria. So the first one is CPU utilization. As I've already said, we should never keep the CPU idle. Our aim is to make the CPU of maximum use. We have to use it. We should never keep the CPU idle, and we have to make busy time to time. So what happens? The CPU utilization can range from 0 to 100%. But in real time systems, what happens is the range is between 40% to 90%. So when it is 40%, we call it as lightly loaded system, and when it is 90%, that is when it uses to the maximum, we call it as heavily loaded system. That is called the CPU utilization. Based on that, we may select the CPU scheduling algorithms. The next criteria is throughput. What is throughput? Throughput is nothing but if the CPU is busily executing processes, then obviously work is being done, right? If the CPU is very busy, or it is running all through the time, it directly indicates, or it is proportional to the work done, right? If some work is done, for that only the CPU is running. So one measure of a work is the number of processes that are completed per time unit. It is called the throughput. So, for example, when we take a long process, this rate may be like one process per unit for a long process, because it takes for a longer time. So the throughput may be one process per unit, or two process per unit, like that. For short transactions, it may take like 10 processes per unit, 12 processes per unit. So it is based on the time taken. So this is called throughput. How many processors in the given time. So that is called throughput unit. Throughput. The next one is turnaround time. Throughput is considering all the process. Here in turnaround time, we consider a particular process. We consider a particular P1. If, for example, P1, P2, P3, P4, and so on, we take the particular P1 and calculate how long the P1 takes. The processor takes process the CPU takes to complete that P1 processor. So that is called turnaround time. And at last, if for example we have 4 processors, at last we sum up all the turnaround time of the 4 processors. Then comes the waiting time. As I already said, if one processor is in the if one processor is running, the other processor will be put into the waiting. That is the waiting state. That is in the queue. So how much time a processor is waiting in the queue, that is also taken into account. Based on that also, the CPU scheduling algorithm is selected. And at last, response time is also considered as a criteria for selecting this scheduling algorithm. So our aim is to maximum to utilize the CPU utilization and maximum throughput, minimum turnaround time, minimum waiting time, and minimum response time. So these are our aims, and we have to take these criteria or these measures into consideration before selecting which algorithm to apply, which will be more efficient. So that is the concept of CPU scheduling. So coming to first come first serve scheduling, we can interpret from its name from its name itself, first come first serve. For example, a ticket counter, a queue in a ticket counter. So the person who is standing in the first in the queue will be served with the ticket, and the first person who will be sent out is also the one who got the ticket standing in the first. So it is as simple as that, first come first served. FCFS scheduling. So the what is the this by this you can actually interpret the disadvantage also. What happens if processor 1 takes a longer time, then the processor next to it will push to a situation that it should wait for a longer time. So this is the main advantage of first come first serve scheduling. Thus that particular point makes this FCFS as a non-efficient algorithm to select. So how this works is, yes, we have P1, P2, P3. So the order, there is the order of arrival, right? P1, P2, P3. That's why it is named as processor 1, processor 2, and processor 3. It will the CPU will get allocated according to the order of the arrival. That it is, for example, suppose that the process arrive in the order P1, P2, and P3. So for P1, the burst time is 24, which is quite longer than the P2 and P3, because P2 and P3 only takes 3 units, but P1 takes 24 units. So what happens here? So we'll see here, a Gantt chart is represented. So first the P1 arrives, which needs 24 units. So it takes about 24 units. Then comes the P2, then comes P3. So what happens here? The P2 and P3 suffers from starving. It is not processed, but it needs only 3, but it has to wait for 24 units to complete. So that is the disadvantage of the first come first serve. So as P1 arrives, it takes 24 units, and next the P2 arrives. In the order of the arrival, it comes as it is only P2. So P2 needs 3 units. So from 24, it takes 3, 24, 25. 25, 26, 27. So 3 units. And P3 again wants 3 units. So it takes from 27 to 30. the waiting time is calculated. How to calculate this waiting time? So the P1 need not to wait for any processor, as it stands first in the queue. So as P1 stands first in the queue, it need not want to wait for any process to complete. So it comes first. So the waiting time is obviously 0, because I mean, it has no need to wait. Then P2. What is the waiting time for P2? P2 should wait for 24 units to complete, because the P1 needs 24 needs to complete its process. So P2 needs 24 units. After 24 units only, P2 will enter. That is the waiting time of P2. Similarly, for P3, P3 has to wait until P1 and P2 completes its process. So in that order, P3 needs 27 units as this waiting time. So for average waiting time, we know that we'll sum up all the waiting time, all the individual waiting times of the process, and we'll be dividing by the number of processors. So we have 3 processors in total. So we are adding 0. The waiting time of P1 plus waiting time of P2, then waiting time of P3 divided by the number of processors, which is 3. So here the average waiting time is about 17 milliseconds. 17 units we have got. So we'll just look for an alternative thing. So in the first thing, we just saw P1, P2, P3 in the order, right? In the second, now we'll see a scenario where the P2 arrives first, the P3 second, and the P2 comes at last. So now what happens here? Now we have represented the Gantt chart in the same order: P2, P3, P1. Okay, I mean, according to the order of arrival. Now to calculate the waiting time, how much waiting time the P2 needs? The P2 needs no waiting time, because it stands first in the queue. So the waiting time of P2 becomes 0. Then the waiting time of P3. What is the waiting time of P3 is? It needs P2 to complete its process, right? So as P2 needs 3 units to complete, P3 has to wait 3 units. So waiting time for P3 is 3. Then comes at last only P1 comes, which is of 24, which is of the burst time 24. Now it needs only 6 units of time. That is, the waiting time will be only 6 milliseconds. It is very minimum, right? So now, considering this waiting times, we calculate the average waiting time. It's the same: P1 plus P2 plus P3 divided by 3, which is 3. Now compare the previous scenario and this scenario. The average waiting time has a major difference. That is, at first we got 17 milliseconds, 17, and now we got only 3, which is a very major difference. So what happens? So it indicates that in first scenario, if it comes this way, we will have a longer waiting time, which will slow down the entire process. So the slowing down of the entire process is called the convoy effect. What happens in the first scenario? What we saw is the P1 takes a very longer time compared to the P2 and P3. So that what happened, the P2 and P3 suffered from starvation. Right? So what happens due to this? The entire system gets slowed down, which is a major disadvantage, and it will not be efficient at all, right? So for that only, we are not considering first FCFS as an efficient algorithm. What by seeing this, you can just interpret what will be the best case, right? The best case is the second one. If it comes in this order, like with minimum burst time to the maximum burst time, then okay, FCFS works well. But if it is in the other way, what we see in the first slide, P1 which contains a longer time, P2 and P3 with less time. In that scenario, it is the worst case. It doesn't work. So this is all about the FCFS. So moving on to the next scheduling, next scheduling algorithm, shortest job first scheduling. So what is shortest first job scheduling is, this algorithm associates with each process the length of processor's next CPU burst. When the CPU is available, it is assigned. So what happens is, wait a minute. Yeah. Now there are four processes: P1, P2, P3, and P4. And looking at the burst time, we have P1 takes 6, P2 takes about 8, P3 takes about 7, and P4 takes about 3. Now what? Now we should look into the now we should never see the arrival order. Now we have to see the burst time. Look into the burst time and uh, find out the minimum among it. What is the minimum among the burst time? The 3, right? 3. 3 corresponds to 3 is which process burst time? That is P4. So P4 arrives first since it has got the lowest burst time. If 2 or 3 processors have the same burst time, then we have to see some FCFS process only. FCFS means first come first serve. In that scenario, we have to put. Here there is only every burst time is distinct, so no problem in that. So we find the minimum, that is 3, which corresponds to P4. So P4 comes first. So it takes about 3 units, 3 milliseconds or 3 units. Then find out the next minimum. Next minimum is 6, right? 6, which corresponds to P1. So next P1 will be in the queue, and it comes into the process. So its waiting time will be 3, and it takes about 6. So 3 plus 6, 9. So yeah, that is all about the P1. Then which is the minimum? P3. So P3 arrives. At last, the max, which has got the maximum burst time, there is P2, which has got 8 units, which is the maximum among the burst time, will arrive at last. So it is basically the SJF is based on the minimal burst time. So this is how we represent the Gantt chart, and the average waiting time will be for P4. Sorry, so for P1, the waiting time is 3. So 3 plus, what is the waiting time of P2? P2 is 16. So 3 plus 16 plus, what is the waiting time of P3? It is 9. Then for P4, it no waiting time. It is 0. Why? Because it stands first in the queue. So it doesn't have any waiting time. So summing up all these 4 and dividing by 4, we get 7 milliseconds. Okay. So this is all about the SJF. So another case, what happens is, consider the same thing, the P1, P2, P3, P4 with the same burst time. Consider it when we consider it for FCFS. If we does the same with the FCFS, what happens is it takes about 10.25 milliseconds, 25 milliseconds as the average waiting time. But here we have got just 7 milliseconds. So we can compare which is efficient. So here SJF is efficient. In which criteria? There is a waiting time criteria. As we've already seen some criteria, right? Waiting time, response time, throughput, then maximum utilization. Here in which criteria it is better? According to the waiting time, SJF is better than FCF in this particular scenario. For this particular problem, the SJF gives the efficient solution. Then, so here also we have preemptive and non-preemptive preemptive scheduling, in which SJF. Okay, in SJF we have 2 criteria, that is preemptive and non-preemptive. And the preemptive SJF scheduling is sometimes called the shortest remaining time first scheduling. What is shortest remaining time first scheduling? So in this thing, we have to consider the arrival time also. For the previous sums and all, we just computed with only with the burst time and we just calculated the waiting time. Here, we have to consider the arrival time also. So, uh, recalling the definition of preemption is that the system has the control. It can terminate, it can forcibly terminate a process from running or before executing. It can put it into the waiting queue, or it can just terminate like that. That is called preemption. So what happens here is seeing the arrival time. Seeing the arrival time, the P1 arrives first. Then what happens? P2 arrives, since the arrival time of P2 is 1. Then then the same way P1 till P3 is allocated. The remaining time, since the P1 has completed only 1 unit, it has to again go through 7 remaining units. So it will again be scheduled in the after P4. So by in calculating this, the average time would be 6.5 milliseconds. So next comes the priority scheduling. So what is this priority? 1 minute. What is mean by the priority scheduling is, priority, we know that in particular order some process will be given priority and some will be in the low priority. The same way here, um, according to the burst time, the maximum the burst time, the lower priority is given. The minimum the burst time, the higher priority is given. So in such a way, this priority scheduling designed, and we will just complete 1 minute. Yes. So we'll see this. So in this, what happens is, according to the priority is given as 3, 1, 4, 5, and 2. So according to the priority, we can see that 1 corresponds to P2. So it arrives first and it completes its burst time. And then what is the priority? 2. 2 corresponds to P5. So P5 arrives and it completes its burst time with 5 units. So it ends at 6 units. Then comes 3, which corresponds to P1. So P1 takes about 10 units and ends at 16th unit. And again 4, which corresponds to P3. So P3 arrives and it completes its 2 units and ends at 18. At last, the priority is given for P4 with 5th priority. So it is coming at the last and it completes its process. So similarly, like we saw in the previous sums, the average waiting time is calculated and it is said to be 8.2 milliseconds. So this is all about the SJF. SJF itself has its divisions like shortest remaining time first and priority scheduling. Priority scheduling is based on the burst time. Okay, coming to round robin. So in round robin, what will happen is each process in the sense P1 is one process, P2 is one process. Similarly, each process will be given a, a particular time quantum. Okay, a time quantum can be from 10 to 100 milliseconds. In that range, we can provide the system can provide any kind of a time quantum. So in within this particular time quantum, um, the process has to be executed. I mean, complete its process. When this particular time has elapsed, the process is preempted. That is forcibly taken out of the process and put it into the ready queue or terminated like that. For example, when we give the time as 3 units, when we give the time as 3 units, but P1 needs 4 units to execute, what happens is the P1 will arrive, but it will run for 3 units because we have given the time quantum as 3. But there is 1 unit remaining, right, for the P1 to complete. What happens is it will be put it into the ready queue. And when the time comes, it will arrive and complete its remaining 1 unit. So that is the concept of round robin. We will be seeing it with an example. So if there are n processes in the ready queue and the time quantum is q, the time quantum in the sense I said like 3, right? That is only q. Then each process gets 1 by n of the CPU time in chunks of at most q times unit at once. No process waits more than n minus 1 of q time units. Then timer interrupts every quantum to schedule next process. Okay. So when the queue is large, that is the time quantum is large, then first in first out is followed. When the time quantum is very small, we can go with this. So for example, we have P1, P2 and P3. First time is 24, 3 and 3. So here the time quantum given is 4 milliseconds. So to represent in the Gantt chart, what we do is P1 first arrives. So what is the time quantum given? It's 4. So it completes its 4 milliseconds, and it has 20 more, right? 20 more remaining, but it is not allowed to complete it. Why? Because the given time quantum is only 4. So when the time is elapsed, when it is about to exceed 4, it is put it into the ready queue. It is put in the ready queue, and the next processor arrives. So what is the next process? P2 is the next process. So it arrives. What it contains burst time 3. So it completes its 3 at a stretch. Why? Because the time quantum is 4 and 3 is less than 4. So no problem and no issues in that. It completes its 3 units at a stretch. So P2 completes at the 7th millisecond. Then P3 arrives. Here also issue is not there because 3 is lesser than 4. So it completes at a stretch at the 10th millisecond. Now what happens? Now again we'll come, I mean, we'll follow the ready queue, right? What is in the ready queue now? P1, right? The P1 is sent to the ready queue, right? Now all the 3 processes has completed. Now we'll go to the ready queue. What is there in the ready queue is we sent this P1, right, for remaining 20 units. So that will be in the ready queue. So the P1 arrives first, arrives at the 4th position, and it takes about 4. Again, 16 units are remaining, right? 16 milliseconds are remaining. Again, it is put into the ready queue. Obviously, now again P1 is also P1 is only going to come. Why? Because we have completed all the P1, P2, P3, and only P1 is in the ready queue. All ready queue. Since the ready queue is empty and P1 is only the element which is going to be present there, P1 is going to come continuously, but with the time quantum 4 milliseconds. So that is why it is divided and not put it at a stretch. That is from 4th to 4, 5, 6, 7, 8. From 4th to 8th position, that is why it is partition, because it allows for 4. If there are like P4, P5, P6, there are more, then the Gantt chart is going to be something different. But here the ready queue is empty and P1 is going to, only P1 is going to fill there. So P1 comes continuously with the time allotted. So typically the higher average turnaround it has higher average turnaround than the short job scheduling, but better response. Okay. Now, here by calculating, average time will be 5.66 milliseconds. How means for P1 it waits for 6 milliseconds. Why? Because 6, it is not 0 or it is not 10. Why? Because 6, because uh, what is the, I mean, position, or what is the time at last when the P1 waited is 10. After that it continuously came, right? So 10, we have to take the 10 and minus that 4, because the first portion of that P1, right? So 4 is subtracted from 10. So the waiting time of P1 becomes 6. Then the P2 waits for 4 milliseconds. That we can obviously see from the Gantt chart. It wants P1 to complete 4 units, so P2 waited for 4. Then P3 waits for 7 milliseconds similarly. So putting together, what happens? The average time, average waiting time becomes 5.66 milliseconds. And this no process is allocated for the CPU for more than one time quantum in a row, unless it is the only runnable process. Here, P1 is the only runnable process at some point of time, right? Next. So here they have given for how many context switches will be there. So when the process time is 10, when the quantum time is the process time is 10, but the quantum time given is 9, is it has to take 9 switches, because 1, 2, 3, 4. It has to be partitioned till 9. 9 partitions are needed after the first arrival. Likewise, if it is 6, then context switch will be 1, because first 6 will be processed. Then the remaining will be 4, right? So again we have to switch. So 4 will be completed within that 2. So context switch needed is only 1. 12. 12, it does not need any context switch because 10 is lesser than 12. So at a stretch it will finish its process. The 80% of the CPU burst should be shorter than the queue. That the queue is shorter than the time quantum. That is here we have seen, right? 10 is lesser than 12, like this. So next we are heading to multi-level queue. So what is multi-level queue is? Um, the waiting queue is there, right? The ready queue is there, right? It will be divided into many sections, separate queues, like Q1, Q2, Q3, based on the types, like interactive, system processors, interactive editing process, batch process, student process, etc. So ready queue is partitioned into two separate, separate queues, many separate queues. One example is foreground. Foreground, which means interactive, and background, which is batch. Then each queue has its own scheduling algorithm. We said that this ready queue will be treated as separate queues based on the types, right? And each type, like foreground process can follow the round robin, and the next process called the batch process can follow FCFS. The next can follow the other priority scheduling. So the each queue can follow its own scheduling process. It is not necessary that every queue in that should follow the same scheduling algorithm. So here that is an advantage. So scheduling must be done between the queues, and we have to see the possibility, like if starvation is there, we have to choose the another algorithm which prevents starvation, like that. So the priority goes like this. First priority is given to system process, then interactive process, interactive editing processes, batch process, then at last the lowest priority is given to the student process. So like as I've already said, system process can independently follow some other scheduling algorithm, and the other can do another algorithm, like that. Then multi-level feedback queue. Before that, in multi-level queue, what happens is no process in the queue, for example, could run unless the queues for system processes, interactive processes, and interactive editing processes were all empty. For example, what it means is, when the process is not completed by the first system processes, interactive process cannot start its process. When the system process becomes empty, the interactive process starts its work. The same way, when interactive process becomes empty, interactive editing process starts its work. If there is any collapse in this kind of thing, then the process gets terminated. So the procedure will be, when the highest priority queue gets empty, then the next is started. So in multi-level feedback queue, it is something contrast to this multi-level queue scheduling, which is, well, already, I mean, in the previous thing, what I said is, if the first queue is not empty, the second cannot start its process. In this, it is not like that. It can move between the queues. Previously, we cannot move between the queues. It is fixed. Only when the first is completed, the second can start. Only when the second is completed, then the third can start. And similarly, it goes on till the last queue. Here, it can move between queues. Here, see, we have 3 queues here. So, first one has 8 milliseconds as its quantum time. The second queue has 16 milliseconds as its quantum time, and third follows FCFS, first come first serve scheduling. So in this, what happens if we put some if the processor entering that quantum 8 should will take about like 17 or like 20. Take for example 20. The P1 contains 20 and it has to enter the quantum 8. What happens is 8 units completed will be completed in the first queue, because quantum time is 8. The remaining 12 will get into the quantum 16. That will finish there and it will go to the FCFS and it follow FCFS, and the process gets completed. So this is how this multi-level feedback queue is working. Then one thing, concept, this is all about the multi-level feedback queue. So main difference in multi-level queue and multi-level feedback queue is, here in multi-level queue, it demands that each queue has to follow separate algorithm, and if and only if the highest priority process gets empty, the next queue has to start its process, and if it interferes or if it gets collapsed, then it will be terminated. But in multi-level feedback, it can move between queues. If the quantum uh, time is elapsed, then it can move to the next queue. which contains a particular quantum time and it has to satisfy it. Then we have to see about the concept of aging, starving and all. So what is starvation? Where the starvation comes is in the priority scheduling. Go back to the priority scheduling. So in this priority scheduling, what happens is, if the priority is given, for example, here the priority is given to the P2, which contains burst time 1. So this is okay. This is efficient. But in the case, what if the P2 contains some 12 or 14, for example, higher values? I mean, the higher values like 14 burst time. What happens is it contains the maximum burst time, right? If P2 is 14, here P2 is 1, but if we consider P2 as 14, what happens? It has the longest duration, right, among the burst time. So due to this, what happens? The following priorities, that is P1, P3, P4, P5, all the others will starve. What does mean by starving? It has to wait for a very longer time. Compared to here in the original example, 1 is given, so it is efficient. It has to wait only for 1. The next priority, P5, has to wait for only 1 unit. But when it is 14, what happens? It has got a longer duration, so it has to wait for a very longer time. So starvation happens, and it again slows down the entire process. So this happens, right? What is the solution for the starvation and this indefinite blocking is aging. So what is meant by aging is a solution for this starving. How come is, when the first priority, I mean the highest priority contains a huge burst time, what happens? The others will starve, right? In that situation, the waiting time taken by the other processors will be increased periodically. The time will be increased periodically. So, the system becomes efficient, and the average waiting time also gets an efficient amount of milliseconds. So that is the concept of aging, starvation, and indefinite blocking. So overall, seeing it as an overall thing, what we have understood is this whole CPU scheduling. What is the aim of this? The major aim is to make the CPU busy all the time and not to make it to be idle, right? We have to make the maximum utilization of the CPU. That is the main aim. Similarly, the system has to make maximum utilization of the hardware also, right? In that situations, or in that instance, disk scheduling is used, which is also called as input output scheduling. So what is the difference between CPU and IO system is, here the CPU, the memory is efficiently used, there the hardware is efficiently used. So we'll again take a glance at this CPU scheduling algorithm. So the major aim is to make the CPU busy. So for that, we use the multi-programming methodologies in which CPU scheduling algorithms helps it to happen. So major thing which drives all these things is the burst time. Burst time is how long a process takes place. That is called as burst time. Because all these FCFS, what all we have seen, we use the burst time to calculate, right? So it plays a very major role. And CPU scheduler is the one which schedules one among the processors. Anyway, if we have n number of processors, even if we have n number of processors, one process has to only one process can be allocated to the CPU at a time. But memory can be all can be at a same memory in the ready state, but while executing, only one process is allocated and the others are put it in the ready queue. So CPU scheduling decisions may take place when a process switches from the running to a waiting state, which where it happens is in that SJF or the priority scheduling. While running the for the remaining time, it will again short job for scheduling and all. We saw that P1 will again go put into the ready queue and it will come at the fourth position, right? So it's like this, which is from the running to the waiting state. There the P1 is transformed from the running to the waiting state. So that is one instance. The other one is which is from the running to a ready state. And then the other one is which is from the waiting to the ready state. Waiting to the ready state is normal. Everything will be the waiting state until it gets into the process, right? Until it is getting to the allocation, right? So that is the things. And the last thing is it gets terminated. And what is the difference between non-preemptive and preemptive? In preemptive, we have the control. We have the not we have the control. The system have the control that it can terminate or put the process into the ready queue forcibly. But in non-preemption, whatever may be the case, whether the time burst time is very long or the waiting time is very long, no other go. It has to complete its process. It has to come out, and the next goes. We cannot forcibly terminate it in the middle of the execution or middle of the processing. Dispatcher is used to give the control of the CPU, which is selected by the short-term scheduler. And scheduling criteria, we have many criteria on the basis which the scheduling algorithms are efficiently selected. For some cases, first come first serve will be efficient. For some, it is not. For some, it needs another efficient algorithm. So it's like that basically. Then here, first thing is CPU utilization. That is a major thing why CPU scheduling is done. We have to make the maximum use of the CPU. We should never make it idle. The next is throughput. How much time it takes to complete their execution per unit time, process per unit time. For example, 2 process per unit time or 3 process unit time. If it's long, then it's it stops with 1 process, 2 process per time. If it's very short transaction, then it takes about 15 process per time or 13 or 10 like that. So our major aim is for maximum CPU utilization, maximum throughput, minimum turnaround time, minimum waiting time, minimum response time. So first come first serve. Yeah, as the name tells, what in the arrival order we'll go by the arrival order, and no preemption occurs. Nothing will interfere and just put it in the ready queue. The whatever the arrival order is there, it has to come, it complete its process, and it should go. So what is the major drawback in this? The worst case is if the first process, which is in the first, which is in the front of that arrival order, if it takes a long time to complete, then the whole system gets slowed down because the coming process, that is in the later part of that arrival order, it should wait for a long time. It should stop for a long time. Due to that, the whole system gets slowed down. So it is called a convoy effect. So this is the major disadvantage of convoy effect. What is the best case of FCS, FCFS in the other hand? When the burst time is in the ascending order. First comes the minimum, the next comes the maximum, like that. If it is in that order, then okay, FCFS works well. But most of the cases, this FCFS won't be efficient enough. FCFS is also used in other cases where we saw in the round robin and priority, not in the priority, short job for scheduling, where when two burst times are same, what happens then to break the tie? What happens? FCFS comes in, which is in the arrive. I mean, which comes first in the arrival order will uh, go first. So waiting time is calculated by how much time the processor needs to wait. That is the best case and worst case of the FCFS. Then shortest job for scheduling. It You can just take an example like in FCFS, as I told, in ticket counter, the whoever is coming first will be served with the ticket. What if in other scenarios, like in some official offices, we are tend to submit our any other files, but at that time we'll be searching a long time, right? In that case, what they'll say, the employee will say that, please sir or madam, just wait and you search that, then we'll attend the next customer. So this will be the case, right? The same thing here, shortest job priority and everything, in the same thing. Burst time. So shortest job first concentrate on the birth time. It is not based on the arrival order. So here, which has got the minimum burst time will come first, and which has got the maximum burst time will come at last. Then shortest job first also has two categories. There is preemptive and non-preemptive, and the shortest remaining time first, what happens is it is a kind of preemption. Preemption comes here. So it takes control over the system. It can forcibly tell the processors to put in the wait ready queue or terminate it completely. Then comes the priority scheduling, which is based on the priority given. The higher priority comes first and the lower priority goes at last. So what is the problem here? The starvation. So low priority processor may never execute, because why? Because the higher if the higher priority, the processor which is given the higher priority has maximum burst time, what happens? The other processor coming next, or the lower priority processor, will start for a long time, will wait for a long time. So it slows down the entire system. So for it, the solution is aging. As time progresses, increase the priority of the process. Then comes round robin. In round robin, the main concept is the time quantum is given. A fixed time quantum is given that can vary from 10 to 100 milliseconds. Within that, a Q will be given. Q is nothing but the time quantum. According to it, it has to process. It comes in the arrival order only. For example, again we'll just, yeah. For example, if we take the quantum time is about 4, until the time is lapsed, that is, until the time becomes 5, it gets processed and it will be sent to the ready queue. And when the right time comes, it gets it. So this happens in shortest job, round robin algorithm. So in 80% of the CPU burst should be shorter than the queue. So it will be very efficient, right? Or else we should get many switches, many context switches will happen, which will really, take much time. So when the quantum time, for example, it is 4, and the burst time is about 1, 2, 3, no problem, because it is less than that. Even 4 is not problem, which is equal to our time quantum. But if it is 7, 8, or the maximum the CPU burst, the context switches gets higher when the time quantum is minimum. In multi-level queue, we have the ready queue is considered as separate type of queues, and each individual queue can follow different scheduling algorithms according to its efficiency or whatever. So one can follow round robin, one can follow FCFS, no other, no problem in that. So the main thing is there is a priority given from higher priority, lower priority. So the system processor takes the highest priority, the student processor gets has the lower priority. So that what happens when system processor gets empty only, the it will be moved to the interactive process. When the highest priority gets empty, it will go to the next, or else it will terminate. In contrast, multi-level feedback, it has multiple queues, but it has got the ability to move between queues. If the time quantums is elapsed, it will be sent to the next queue. So this is all about the CPU scheduling.